Optimization. Right. Why would they yell about optimization? Optimization can be a good thing. Yeah, you can take courses in optimization when you go to college. And up until now, we've taken the derivative and we've used it to graph, basically, right? We're pretty good at graphing right now using the first and second derivatives. But now we're going to move on and apply differentiation in derivatives, not to find max and min of y values, just a function of i's. Or we're actually going to maximize or minimize quantities that we find in life. So an optimization problem is a problem where you're trying to maximize or minimize some quantity. And I want you guys to try to think about, like, if you were in economics, let's say, what's something that you might want to maximize?
Money. Profit.
Profit. Beautiful. What's something you might want to minimize? Spending costs, right? Very good. What's that? Oh.
As a rock.
I don't know about that. But yeah, think about something in your own lives that you would like to maximize or minimize. You'd like to maximize your average. What is something maybe you want to minimize?
Failure.
Test, school time, maximize homework.
No, it's not what it said.
Jillian said that. All right. So what I want to do, guys, is take our knowledge. We already know how to maximize and minimize a function, and we're going to start by reviewing that together. And then we're going to apply it to word problems. And these are called optimization problems, and there's nothing to be afraid of. I know people get afraid of word problems, but there's no reason to be. Because once we review how to get the max and the min of a function, we're just going to have a slight little shift over to the real world, and we'll solve word problems. All right, so for the first part of our do now, I want to find the absolute minimum value of a function over a closed interval. Think about where the absolute min could occur and check out the y coordinates at those values. Can the absolute extrema occur? All right. So, since the absolute extrema have to occur at either a critical value or at an endpoint, what should we do first? Find the derivative, because that's what we need to get the critical value. What's the derivative? 3x squared minus 3. Nice. All right. Now this is always going to be defined, so critical values are just going to be where it equals 0. So when you set this equal to 0, did you factor it? 3x equal that? X squared minus 1. Okay. Now what values of x make the derivative 0? What are my critical values? Yes. Well, yeah, but if you're looking for the minimum value of the function on the interval from 0 to 3, negative 1's not in that interval, so we're not going to look at it. It can't happen there. That's not in the interval. So we'll only check out the y value at 0, 1, and 3. It has to be at one of those, right? At 0, what's y? How about at 1? Nice. And how about at 3? 23? Good. So of those y values, what is the absolute min? 3. So the absolute min, that's what we asked for, right? Yep. So the absolute min is 3, and it occurs at x equals 1. Nice. Good, but you should know you really want to know that the absolute max min is the y value and occurs at the x value. So if you're asked to find the absolute maximum over a closed interval, no problem, right? Well, we've also had some techniques to find relative extrema. We've had the first derivative test and the second derivative test. So I want to start out by finding the relative max of the function 4x minus x squared using the first derivative test for extrema. Oops. So get your first derivative and get the critical values and mark them off. I kind of made the sign chart for you, but just didn't mark it off. All right, so what's the derivative? 4 minus 2x, and so the critical values when it's 0 undefined would be what? X equals 2. So that's the only value of x where the first derivative could change sign. Give me a value less than 2. 1. Okay. F prime of 1, would that be positive or negative? Be positive, right? Because 4 minus 2 times 1. Okay. Give me a number greater than 2. Right. Okay. You plug that into the derivative, positive or negative? Negative. Okay, so looking at that sign chart, it goes from positive to negative at 2. Let me just make that little sign chart up here. F prime. Okay, so since it goes from positive to negative, F has a relative max at x equals 2, right? Now, that's nice. It's a relative max. But if you look at this sign chart, I wish I knew if it was an absolute max. Right? Wouldn't that be great? Because with these optimization problems, you're really going to be looking for an absolute max, and absolute min. So we use the first derivative test for extrema, and if you look at it, where is the first derivative positive? What values of x? Less than 2. For values of x less than 2, you notice how the derivative is always positive? And for what values of x is the first derivative negative? Think about the function. When x is less than 2, the derivative is always positive. What does that mean about the function? It's increasing. I'll do this for the kids at home, right? And then when you get after 2, it's always decreasing. Do we have to worry that it's going to shoot back up again somewhere else? No, right? Because it's always increasing when x is less than 2 and decreasing when x is greater than 2. So not only does f have a relative max at x equals 2, it has an absolute max at x equals 2. All right, so we use the first derivative test for extrema, and we usually just use that to find relative extrema, but we can use it to find absolute extrema. Now I want to go back and just review the second derivative test. I want you to find the relative min of the function 6x squared minus 12x using the second derivative test for extrema. Remember, you find out where the first derivative is 0, and that just tells you where you have a horizontal tangent, but you don't know what it is, right? But you pop that number into the second derivative, and if it's positive, you have a min. If it's negative, you have a max. Remember that? So first thing you got to do for the second derivative test for extrema is find out where the first derivative is 0. So you've got your first derivative, 12x minus 12. All right, and you set it equal to 0 with the second derivative test for extrema. You get x equals 1. So now you know at 1 you have a horizontal tangent, but you want to know whether it's concave up or down at 1 to see what type of extrema you have. So you have to get the second derivative, 2. And what is the second derivative of this function? 12. It's always 12. So the second derivative at 1 is equal to 12. What does that tell us about the concavity at 1? Is it concave up or down? Up, because 12 is positive, right? That means my function is concave up there. We already knew it at a horizontal tangent. So what do we have at x equals 1? A relative min. So we have a relative min at x equals 1. Okay. Now, because we just found out that the first derivative at 1 is 0, the second derivative, not only is it just positive at 1, it's always positive 12. It's positive for all values of x. So think about your graph. You know you got a min at 1, and you know it's always concave up. This function, not only does it have a relative min at x equals 1, if you've got a min and the function's always concave up, it has an absolute min at x equals 1. Any questions? So if you have a closed interval, you want the max or min, the absolute max or min, no problem. Just check out the y coordinates at the critical values and the endpoints. But if it's not a closed interval, you know, you're going to use your first or second derivative tests to find the relative max or min, but then it's going to wind up being the absolute. You'll see it once we get into the problems. So that's all you're going to have to do is use your first or second derivative test to find the max or the min. It's usually not going to be close. What's wrong? Aha! All right, so we're going to take this, since we know how to find the max and the min of a function, we can do it for word problems. No biggie. There are basically 5 steps to solve an optimization problem. Now, an optimization problem, you're going to know you have one because they're going to say find the largest area. Find the least cost. Or they're going to ask you for the greatest or the smallest value of some quantity. So the first thing you want to do is draw a diagram and label it. If appropriate. Sometimes there's nothing to draw. But here's the big thing. Whatever they're asking you to optimize, that's what you need a formula for. If they say maximize the profit or find the maximum profit, you need a formula for profit. If they say maximize area, you need a formula for area. Okay, that's the big thing. But then, before you can get to the calculus part, the good part, you got to get that formula in one variable. Okay? So if you have 2 variables, you got to get rid of them. Get rid of one of them. And the way you're going to do that is with another equation. You're going to have another equation you're going to be able to write and do some kind of a substitution. Oh, that's not bad. You know, you've solved systems where you solve for y in one equation and you pop it into y in the other.
Do it physics.
Oh, so you do it all the time. You love that. Yeah. There's some prolonged exposure produces liking, like in psychology. Yeah, something like that, right? Yeah. So now you love it. Yeah, you feed kids peas all the time when they're little. They learn to love peas. All right. Now, so you get this equation for whatever it is in one variable, and you want to look at it and say, okay, for what values will my answer make sense? You know, like if x represents time or something, you want to make sure that your answer is going to be positive. You make a little note to yourself, okay, my answer better be some positive value, or whatever it is. But then comes the good part. So you have this equation, you just find out where it has a max or a min using the first or second derivative test. Unless it's a closed interval, then you can just check the endpoints and the critical values. That's it. This is the fun part. So you just got to get your equation in one variable, and you're just finding the max or the min. Ready? You like pigs? Yeah. Gotta like pigs. All right, look at your pig. You see your pig? Oh, look at him. He's so happy. He was going. He stopped. So there's this farmer friend of mine, and he has a neighbor, and his neighbor said, listen, Jed, I have 100, that's just came to me, 100 yards of fencing left over from some other project. You want it? He's like, yeah. I want to build a little pen for my pig. I'm going to put it on the side of the barn. So I don't need a fence on the side of the barn, but I need to have fencing here, here, and here. 100 yards of fencing, right? But I love this pig, and I want this pig to have as much room to run around as possible. I want to maximize the area of this pen using this 100 yards of fencing. So I could just run out there, forget about calculus, and make a pen. Like I could just, like, is it even really going to matter? What if I just take 1 yard of fencing? I don't know. Is it really going to make a difference? Or what would this length be if I have 100 yards altogether? 98. What would his area be? 98 square yards. That's pretty good. Do you think I can make it any better? No, that's it. What would give me another possibility? So I just gave you one possibility. Okay, so you're saying, well, wait a minute. If this is 2, and then this side is 2, yeah, it would be 96. What would that area be if it was a 2 by 96? I got to see it separately. 192 square yards. Oh. Okay. Well, you got 3 sides of fencing you got to do it. So you're thinking 33, 33. So what would that area be? What's 33 times 33? Okay, so you can see it's definitely going to make a difference how much area this little piggy has to play in. Well, do you want to go out there and just keep taking the fence and, like, you know, do you ever dig the holes for the fence post? And then, oh, no, we could have done better. Take it up. Let's do it again. Let's try something else. You do not want this pig to complain, and he's going to know if you do not get him a lot of area. All right. He just is trying to show you he needs room. Okay, so our first step in finding the optimal dimensions for this pen is to label anything that we need to label. So what do you want to call this length? X? So this guy over here, this length is X. What do you want to call this other dimension? Y. Okay. So that's your first step. You draw a little, label whatever you can. Now, here comes the next thing. You need a formula for whatever it is you wish to optimize. What are we trying to optimize? Area. Do you guys know the area of a rectangle? Okay, area of a rectangle is length times width. So in this case, what's the area going to be? X times Y. Beautiful. Okay. Next step, step 3. You got to get that, before you can take derivatives or anything, it's got to be in one variable. Right now it's X times Y, that's in terms of 2 variables. So I need to get it in terms of one variable. And when that happens, you're going to need another equation that you can use to help substitute into that one. Is there any other equation you can write with X and Y? Perimeter, okay. Give me, say it, Sydney. 2x plus y equals 100. Does that make sense? X plus y plus x, that had to add up to 100. So that's the second equation. So when whatever your formula that you're trying to optimize is in terms of 2 variables, you're going to need another equation according to the constraints or limitations of the problem. That's the other equation that you're going to use to substitute. So what do you want to solve for, x or y? Y, right? Easier. So what does y equal? 100 minus 2x. Good. So that's going to allow us to get our area in terms of one variable. So area is equal to x times 100 minus 2x. Nice, right? All right, you know, we will get to the point where we'll take the derivative and find the max. That's the easy part. Let's just clean it up a little. Let's just distribute. So the area is equal to 100x minus 2x squared. And just for what values of x I'm going to get a value of x in a minute. And I just want to know for what values of x does this problem make sense? Can x be negative? No. So x has got to be somewhere. If it's 0, I'll have an area of 0. That would be sad if you make x the area. I mean, technically, I guess it could be 0, but then poor Piggy has a minimum area. What is the maximum value of x? Well, you have 100 yards to deal with. Well, if you make this 99, you got an x on the other side, too. 50. 50, and if you make x 50, what's left for y? 0, right? So, yeah, x could go from, so we're looking for a number, not 0 or 50, because that's going to make the area 0. That'd be silly. We're hoping that our answer is going to be somewhere in between 0 and 50, or we did something very wrong. All right, here's the fun part. To find the max, if I just gave you this function, instead of calling it f of x, I called it a for area, and I said find the max, what would you do? You'd get the derivative, right? Anytime you want to find a max or a min, you get the derivative. All right, 100 minus 4x. Now, no matter what test you're doing, you're going to have to find out where what your critical values are. So you want to know where is the derivative equal to 0, because that's always defined. X equals 25. Now, I would have done the same thing if I was looking for a minimum, right? So I really want to make sure that this is going to give me a maximum area. Do you want to do the first derivative test or the second derivative test? First? Yeah, that's up to you. You want to do it first? Okay. And I know that x can't be a number less than 0, so I'm just starting at 0. So I'm only going to mark it off here at 25. Okay, give me a number between 0 and 25. Okay, they're both good. If you plug that into the first derivative, is it positive or negative? Positive. If you take a number greater than 25, it's going to be negative. It's always going to be negative, right? So at 25, do we have a max or a min? A max. And not only do we know we have a max, it's not only just a relative max at x equals 25, it's absolute, because it's always increasing when x is less than 25, right? Your derivative is positive when x is less than 25. Okay, because for values of x, I'm going to write absolute here at x equals 25. The reason is because for values of x less than 25, the derivative is always positive. And for values of x greater than 25, it's always negative. So your function's always increasing when x is less than 25, and it's always decreasing when x is greater than 25. So that value has to be a max, absolute max. That's exactly right. You could compare them. Okay, now, is this what they asked us for? You always want to go back, any word problem, did I answer the question? So I know making x 25 will give me the greatest area. Yeah, they want the dimensions. So just to finish it up, so the dimensions, and Audrey, you were right. I wasn't purposely, I was kind of ignoring you because I didn't want you to think you can just do this without calculus. That made me sad. You got that right. So yeah, the optimal dimension, you're going to have a maximum area if we let x equal, we said 25 yards, and I'm sorry, what was y? 50, right? Because y, remember, was 100 minus 2x. And that maximum area, how much area did we get this little guy? They didn't ask for it, but what is 25 times 50? 1,000 something. 1,000. So it's going to have a maximum area of 1,250 square yards if we make these just the dimension. Isn't that cool? So the pig doesn't have just 98 square yards to play in. It's got a lot. Maybe we'll get him a friend. Get in there. Something good. All right. So that one you guessed. But I've got one, guys, I don't know that you're going to just be able to guess. The box problem. This is a classic problem. That's why I put in little quotes. I don't know if you're going to be able to guess. This is, I measured it before class, 20 centimeters. Sorry, kids at home, you can't see it. I'm showing a piece of paper. 20 centimeters by 25 centimeters, okay? Now, I want to create a box by cutting squares out of the corners and folding up the sides. I'll show you one that I did. Yeah. Here's one. We cut out squares and we folded up the sides. And you can make a little box, right? And that box is going to have volume. Anyone? Oops, sorry. Well, I'm just wondering if I should make smaller squares, bigger squares. I want the volume to be as great as possible. That's better. I don't know if you can see that. Maybe that. Any, like, if this is a 20 by 25 centimeter piece of cardboard, what size squares should I cut out? Any sense of like around what you think it's going to be? Well, yeah, because less than 20, or because one box then would fill up the whole side. Right, I wouldn't even be able to do it. Give me an idea of something. I'm gonna make it. Give me a number. That's a number of centimeters. 5, 13. Well, is it even possible? If I make a square 13 centimeters, if I cut out, that's going to take me more than halfway. It's got to be less than 10, or I'm not going to be able to cut a square out of both sides. So give me a number less than 10 that you think.
9. She likes it.
Well, she's wrong, so it's all right to let her be a little. You want me to do 8? Why? She said 9? That's a lot. How much would that leave in the middle? It'd only leave 2 centimeters. You want to go with that? Great. Wait, our phone's ringing. I need. Where's my little phone? All right. The box that we have, we decided as a class to cut out 7 the squares. Well, we had to listen to somebody. We cut out squares of 7 by 7 centimeters, and we round up with a box that has this kind of a volume here. I'm showing something, you guys can't get it. And we're wondering, I'm not recording? Oh, yeah, no, I am. How do you, okay, that's the length times width times height. So I don't know if this one's going to be better than the one that's smaller. You still think it's going to be around 7 or any other? Okay, we'll see. We'll see. So that would be something that would be harder to just guess, right? So we're going to start out by drawing a diagram whenever it's possible. So this was 25 centimeters to begin with. Why did they do that? Okay. Now, we're cutting corners out of this. We're cutting squares out of the corners. So I'm going to call this X and that X. That's what we're trying to figure out is what size squares we should cut out. Okay, now I need a formula for what I'm trying to optimize. What are we trying to optimize? The volume. Now, volume you just told me was what? Length times width times height. Now, the length of the whole piece of paper before I cut out the squares was 25. But when I cut it out and fold it up, now what's the length? 25 minus 2x. Because, right, we're cutting out an x out of each side, so when we fold it up, we only have 25 minus 2x. What about the other side? It was 20, but we cut out the x's, 20 minus 2x. Now, what's the height of the box going to be? X, right? It's whatever, you see it? Kids at home, sorry, this is where maybe you should have come to school today. All right. All right, now, the good news is, look at our equation for the volume. With what? One variable. We don't need another equation to substitute in, so let's just clean it up and take the derivative, blah, 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 and get the max. This is fun. What the kids are saying. All right, we're going to multiply it out. We'll multiply through by the x afterwards. Let's FOIL out the first 2 factors. What do we get? 500 minus 50x minus 40x, 4x squared. And I still have that x there. I'm squeezing that in over there. Okay, we're going to distribute the x, and I'd also at the same time like to combine the negative 50x and the minus 40x. So, and we're distributing the x, so what do we got? 500x minus 90x squared. All right. What did I miss? Like the, okay, let's get the derivative. All right, derivative. Minus 180x. All right, and well, at least it's always defined. We set it equal to 0. We can factor out a 4. I will tell you that. So we could factor out the 4. I'm going to change the order, right? We'll just rewrite in the opposite order. So 4 goes into the 12x squared, 3x squared. 4 goes into the negative 180x, negative 45x. How about 4 into 500? Good. All right, so we're setting the derivative equal to 0. We tried to factor the best we could. Whoops, tripping here. And, but, you know, we still have to solve this quadratic. Let me tell you, kids, you can't always factor. Yes, x equals negative b plus or minus the square root quadratic formula. That's right. All right. Negative b, what do we got for that? Plus or minus the square root. B squared, you know what 45 squared is? Because it's negative 45, but you squared it's positive. I'll tell you. 2025. Thank you. That was good. Now, how does it go? The b squared minus 4ac. So minus 4 times 3 times 125 all over 2a. So all over 6. Good. That's the b squared, so negative 45 squared. All right. This minus 4ac, what's 4 times 125? 500 times 3? 1,500. So we've got 45 plus or minus the square root of 2025 minus 1,500 all over 6. What is 2025 minus 1,500? 525 is good enough. Now, we could maybe break it down. Do you want to break it down? Do you want to break that, or do you want to leave it as is? Because either way, we're going to the calculator at this point. Leave it? All right, I need one person to tell me what 45 minus the square root of 525 is over 6. I need somebody else, because we got 2 answers here. This is a problem. Tell me what 45 plus the square root of 525 all over 6 is. Yeah, tell me the 3 places after the decimal. No way. Did you divide by 6? Thank you. I'm listening to you. Give me 3 places after decimal. So 3 point. That's right. Maybe you didn't close the square root or something. Just close the parentheses for that. And the other one? $318 or $319? Okay. Oh no, 2 answers. Do you remember when we were talking about how big x could be, what values make sense? It couldn't be bigger than 10, right? Remember that x, the side of our square, can't be greater than 10. So we get to reject that. And then we would just have to make sure that this is indeed a max and not a min. So if we made, do you guys like the first derivative better?
Yeah.
All right, what's the second derivative then? Oh, we don't need the second derivative. You said first derivative. I'm sorry about that. Ew, but look what you got to plug it into your way with the first derivative. So if you make a sign chart, you mark it off at, because it only has to go up to 10. You don't have to worry about that. And it's got to be greater than 0. But the 3 point, what do we get, kids? 3.681. Nobody guessed that anywhere near that, did they? That's gonna give us. All right, it's positive, it's negative. That is how many centimeters we should cut out. That should be the length of the side of the square. So we should cut out to give us a maximum volume.
At the end of the day, leave all computers on. Do not shut down. The tech department will be working on an upgrade. Also,
Remember,
after 15 today.
4 problems in the book this weekend. Enjoy them.